now going to develop the description of collisions, and we're doing this, of course, in a classical manner, and the primary thing that collisions are used for is studying subatomic particles. So obviously there's more complications if you consider subatomic particles because we're not using quantum mechanical effects, and we're not looking at, well, often now we have to use quantum field theory to get a complete description of subatomic particle collisions. But the fundamentals and the concept that we're going to define here, the cross section, does in fact translate over to studies that incorporate these things, and the definitions hold for the most part. So even though there is more advanced theory that is necessary to describe these collisions, this gives us the foundation. So these are really useful for studying subatomic particles. In principle, you could study other things, but there's often easier ways. So there's an XKCD comic about how physicists just study frogs by smashing them together, and this is why they don't let physicists do biology. You actually could learn something about the structure of the frog by colliding two frogs together. What you would see is that it is not isotropic as a function of radius, because you wouldn't necessarily be able to tell the orientation of the incoming frogs. You wouldn't get the detailed structure of the frog, but you could in fact see that there is a radial dependence of density on structure, and you could even detect that the frogs are lumpy, that it's not that it is not an isotropic distribution around the center of mass. But of course, that's not how we study frogs, because we can actually see frogs and we have many other tools at our disposal. When it comes to studying subatomic particles, we don't have a lot of other tools at our disposal. So we don't really have any other tools at our disposal. So what we do is that we smash these particles together and destroy them, and see what happens when you destroy them. And we can measure the distribution of all sorts of, the azimuthal distribution of all sorts of these things. We can measure how the cross-section changes, what comes out of these collisions changes as you look in different regions spatially, or as you change the energy of the incoming particles. But we can't see directly, so we have to infer. Now, when we study things like this by smashing them together, we can't learn a lot from a single collision. All we see is where we usually call one thing the target and the other the projectile, and often the target is at rest and the projectile is moving. So when you have, and all that you see is that you see something coming in and you see something coming out, and you can see, sometimes you can see where stuff comes out and measure its energies. Usually you know what's the energy of the incoming projectile is. Usually you at least assume that the target is at rest or close to it. And that doesn't give you very much information. We usually study ensembles of these collisions, lots of them, and we look at the statistical distribution of all of the collisions. And we talk about the scattering angle and the impact parameter. And these are, in fact, terms that carry over into the quantum regime, or really it's just a definition. So here we're going to have our target. Now, strictly speaking, you don't have to have one of them at rest. Here we're going to have our projectile. And this is either the target and the projectile themselves, or if they're extended objects, it may be the center of mass of the target and the projectile. And the projectile is coming in along with a certain momentum, and the target is coming in with a certain momentum. the target is, you can draw a line that is parallel to the projectile's momentum going through the center of mass of the target, and pretend that this is a straight line. I am a physicist, so I am not the world's greatest artist. And the impact parameter is, we use the variable b, and the impact parameter is the distance between the centers of masses of the projectile and the target. And then what actually happens to the projectile, we will first consider a case where the projectile and the target are not modified by the collision. They just, they're just deflected. So the projectile comes in. So here, this is the trajectory of the projectile. It is going to be deflected by the target. And so at some point near the target, it's going to have some structure. And we can define that, we define this angle theta as the scattering angle. And let me write over here that this guy is the impact parameter. And these concepts carry over even if we're talking about more complicated projectiles and targets, and even if we're talking about things happening at the quantum mechanical level. And you can have the scattering angle if you talk about the scattering angle if the projectile more or less stays intact. So then we have restrictions on the scattering angle. So first of all, note that if it is 0, there is no scattering. The projectile just goes straight and is not deflected by the target. This happens if there's either no interaction between the projectile and the target, or if the projectile doesn't even get close enough to interact with the target. But then your scattering angle can vary. Okay, it can be 0 at the smallest, so you can't take any ranges, but it could be 0 if it's undeflected. And if it is turned around exactly 180 degrees, the scattering angle is pi. Scattering angles greater than pi don't make sense, because that would imply that the projectile goes in like this, and what that would mean is that actually your impact parameter were this way, and you could define that equally well as having a scattering angle of less than pi. Now, you can think about how this might happen if, for instance, your projectile and your target are attracted or repelled by the Coulomb force. And as was the case for Rutherford scattering, leading to the discovery of nuclei. And the impact parameter, so this is the distance of closest approach if there is no interaction between the projectile and the target. Often an impact parameter of 0 will correspond to a scattering of pi, so they just bounce right off of each other. And in principle, there is a unique impact parameter for each angle theta. So often what you are looking for is theta is the scattering angle as a function of the impact parameter. The scattering angle typically can be measured, but the impact parameter cannot be, at least not directly, because when you're talking about subatomic particles, we can't measure their positions to something on the order of their radii. If we're talking about nuclei, that's 10 to the negative 15th meters. We simply cannot measure their positions before a collision that accurately. Now, and then usually there is a one-to-one relationship between the scattering angle and the impact parameter. Now we can, now I want to mention, just because my field does this, we have constraints on the impact parameter. What we do is that we look at the total, I do high energy nuclear physics. We smash two nuclei together and you get a lot of particles, and we make an assumption that is strongly based in data and based on decades of comparisons between data and models. We make an assumption that the more particles come out of a collision, the smaller the impact parameter was, and on average that is true. So when you have a lot of particles, you can at least constrain the impact parameter, but we're still not measuring it. We're looking at distribution. So often when you do collisions, you are looking at the statistical properties of collections of collisions. And then what we're going to do is define a scattering cross-section. And this is an effective area for the projectile and the target. So, because we are talking about probabilities, in most cases. So if you have your target, your total target, so you have like a thin foil of some type of metal, and then you're going to have something, if you're talking about a foil, you're going to have a somewhat random distribution of actual targets, target nuclei in that foil. And they each have some area, so they will each have a cross-section. What we're going to start, in this chapter, we're going to oscillate between describing things with a picture in our head that we've got spheres colliding. That picture is going to serve you well throughout the chapter. So we'll develop our picture imagining that we're colliding spheres, but we're going to generalize the concepts so that we can actually talk about more than just spheres. Our object doesn't need to be a sphere, but we're going to use the same equations to define a cross-section. Then we want to quantify the properties of this target. And here I'm going to apologize because I find the book's subscripts maybe a little lacking, but I'm going to stick with them in order to follow the book. Sometimes I'll write it out fully because I find the acronyms not the most useful, but I'll try to write out something so that you can at least figure out, so it follows the book. I think that, often he chooses the first three letters of the word, and it doesn't really tell you what that means. And for instance, the scattering cross-section, he uses subscript SC. Well, that's not very enlightening, at least it wasn't to me. Okay, so we're going to quantify the properties of this target. The number of, let me distinguish, in this, let's assume you have a foil. So we want the number of target nuclei inside of the target foil. So the number of targets is going to be the density of targets times the cross-sectional area of the foil. Where what we're after here is, so the cross-sectional area of one target nucleus, area of one nucleus. Now, the book doesn't describe it as explicitly for nuclei, but I think it helps to have a picture in your head. Would be, Here we're imagining them to be little solid spheres. Pi times the radius squared. And area of all targets in the foil. Let me say all. Let me just be explicit here. We will just imagine that we're talking only about nuclei. The number of nuclei. So the area of all nuclei is then going to be the number of targets times the area of the foil. So the number of the number density of the nuclei times the area of the foil times the cross-sectional area of a given of each individual nucleus. So then the probability that our projectile is going to hit one of those nuclei is going to be the area of nuclei over the total area. And that's going to be n targets times A times sigma divided by A. Or the number density of targets times the cross-sectional area of one target. And then the number of scattered projectiles this NSC is the number of incident projectiles times the probability of getting a hit for each projectile. So this here, we use the variable sigma, is the effective area of the target for interacting with the projectile. So we're imagining it as a cross-sectional area, but it could be an effective cross-sectional area. For instance, if you think just about the nuclei themselves are not hard spheres, they have some actual distribution that falls off and as you get closer to the edge. And then it's important to note we actually can either measure or control the number of incident projectiles. We can measure the density of targets, and we can measure the number of scattered projectiles, which means that we can use that because we can measure these two things and control or measure this, and that means that we can get this cross section. I say control or measure because sometimes you have a source that you can control, and sometimes you have a source and you can't control it, but you can at least measure it. So then we can look at an example. And this is, well, I wish that these books would maybe choose examples that were, well, I guess we're talking about projectiles anyways, but maybe a little less morbid. Shooting crows in an oak tree. So you can estimate, I hate the fact that this used non-SI units, but the units all cancel out, so it doesn't matter much anyways. It's just on principle, I feel unpure when I am using something other than SI units. So we can estimate the area of a crow is half of a cubic foot. So that's like this big. So we will say that the area of our target is around half a foot squared, and we have a total area of the oak tree of about 150 feet squared. That's the cross-sectional area if you look at the oak tree. And then we will assume that the number of targets, you're shooting at crows, the number of targets is about 50 crows, and that you shoot 60 bullets into the oak tree. And then the question is how many hit or how many are scattered. So the number scattered, the number of bullets that are scattered off of the crows or hit the crows, is the number incident, 60, times the probability of finding one of those bullets, finding a crow, which is the total number of targets divided by the area times the area of one target. And because we're looking at the ratio of the geometric areas, the area, these horrible units cancel out. So the fact that we used impure units doesn't really matter. And you see that you get 10, that you would shoot 10 crows like that. Now, it is often useful, this imagines that you have a specific number of projectiles. We often have a source and we are sending a beam of projectiles at our target, so we define a rate. So the rate is the number of incident projectiles over a given rate of time. And then we get, and this is the rate of the incident projectiles. And then we have a rate of scattered projectiles, which is the number scattered divided by that same change in time. So this becomes a rate, and so we're basically dividing here by delta t on this side and this side. And then what we get is that the rate scattered is equal to the rate incident times the number of number density, times the density, the area density of targets, the number density of targets times the cross-sectional area of a single target. All right. So this is often the version that we will actually use, although keep this in mind as well. Sometimes it is more convenient to use a number, and sometimes it is more convenient to use a rate. Now, the SI unit of area of this cross-section is a meter squared, but when we're talking about subatomic particles, a meter squared is huge. So we are going to define a different unit. We're going to define the barn, and the barn is 10 to the negative 28th meters squared. And this was actually created during World War II as a way to obscure, they called it a barn because they wanted to obscure the fact that they were talking about nuclear targets. We can then look at an example. This is 14.2, scattering of neutrons off of an aluminum foil. So we have incident neutrons, and we are going to have the incident neutrons come in, 10 to the 4th of them, and we will have the scattering cross-section for the neutron off of the aluminum as 1.5 barns. Hang on. Yes, 1.5 barns. And then we have a width of the target of 0.10 millimeters. So now we know how wide the target is. That tells us the density in cross-sectional area because we know we can find the density of aluminum, and then we can get the number density of aluminum if you have a 0.1 millimeter thick foil. So the question is, what is the number density in the target? It is going to be the density of the target times the width of the target. So that will give you the density per unit area divided by the mass of one single molecule of aluminum. That gives you the number density per unit area. So the density of aluminum is 2.7 times 10 to the third kilograms per meter cubed. And then we multiply by 10 to the negative fourth meters. So this gives me a kilogram per meter cubed, per meter squared. And then 27 atomic mass units times 1.66 times 10 to the negative 27th kilograms per atomic mass unit. And then we'll just double check our units here. We want to get units of inverse meters squared. So here, this becomes a 2, and we get inverse meters squared. Here I have 2.7 divided by 27, so I'm going to times 1.66, so I'm going to get, well, these numbers will make a nice round number. Here I've got 10 to the 3 times 10 to the negative 4. This becomes 10 to the negative 1. And here I have a 10 to the negative 27, so I'm going to get something on the order of 10 to the negative 26, except I've got 10 to the negative 25 from this guy right here, because this is another order of magnitude. And then when you plug the numbers in, 10 to the 6 times 10 to the 24th inverse meters. Now, why am I showing you the reason I'm showing you my thought process for double checking the order of magnitude is because it's really useful. So you guys are all used to using calculators all the time, and calculators are lovely. It is very easy to plug numbers in incorrectly or to put the parentheses in the wrong spot. So what I find it useful to do is to check orders of magnitude and make sure your answer ends up about the right order of magnitude, just because it's very easy to plug numbers into a calculator incorrectly. Also, you can get, sometimes when you're working with really large or very small orders of magnitude, it works out better to collect all the factors of 10 to the whatever and get that out in front, because most calculators can divide numbers on the order of 1 and 10. Those it handles fine, but it doesn't always handle 10 to the negative 27th very well. Okay, so then we can calculate the number of scattered neutrons, which is the number of incident neutrons times the number density in the target times the cross-section, the cross-sectional area of one of the targets. It's really the effective cross-sectional area for one of the projectiles hitting one of the targets. And we get 10 to the 4 times 6 times 10 to the 24 inverse meters times 1.5 barns, and a barn is 10 to the negative 28 meters squared, and all of this works out to be 9. So let's collect our orders of magnitude. We've got 10 to the 4 plus 10 to the 24 is 10 to the 28, and that is multiplied by 10 to the negative 28. So all of the powers of 10 cancel out. And we are left with 6 times 1.5, which is 9. Now, in most actual problems that you'll come across, you would not have such nice, neat numbers, but this is, of course, a textbook problem. So then we can generalize, as promised, these concepts to scattering to other forms of scattering. So the first thing that we want to do is that we were so far treating these things like, the target has some structure, maybe it's a circle, but we weren't worrying about the projectile. Of course, if you are assuming that your target is a sphere, then it's a logical assumption that your projectile is also a sphere. Now, when I drew my diagram, I was a little more general than the book's first diagram anyhow. So we have our impact parameter here, and assume that I have drawn that carefully and that this is in the center. And then if you want to look at the cross-sectional area for this thing hitting that thing, it is, we will call the target 2 and the projectile 1. And the book mostly follows that notation. And then your cross-sectional area for the target hitting the projectile is not just pi r2 squared, but it is pi r1 plus r2 quantity squared. So that's the effective area for the target to hit the projectile. That is that if your projectile is large, if your target is large, it's more likely to hit the projectile, and if your projectile is large, it's more likely to hit the projectile. So what you're really considering here to get at this, here is your projectile, and it's got some center, and then you can get, as long as those two, as long as the two spheres are barely touching, you will actually get some interaction between the two of them, which means that your effective area for your target is the one swept out by how far away the projectile could be and still hit the target. Again, my artistic skills are lacking. That did not have a constant radius. So something like this, because anywhere in here I could put my projectile and I would still have an interaction. So when my projectile and my target both have some extent, then I have a slightly larger effective area for my my target. So I'm going to follow the next example, but I do think that this is also a little bit of a deviation, and it's hiding things to call it an example because it's somewhat of a different application. So we will look at the mean free path of molecules of air. And here we're going to be making the approximation that there's no difference between nitrogen and oxygen, and that they behave like hard spheres with an effective radius of around 0.15 nanometers. Now, we know that they're not exactly spheres, but they rotate quickly, and so when they're constantly moving and rotating, you can't necessarily detect the structure inside of the molecule of air, and if you do a scattering experiment, you are still looking at an effective area. All right, so we will look at we'll derive an equation for the mean free path. The mean free path is how far a molecule of air can travel without a collision. You have this concept of mean free path in various other areas as well. The mean free path of a gas is going to determine its conduct, or a liquid, any fluid, is going to determine its conductivity, its viscosity, and the diffusion rates. It is how long something can travel before it smacks into something. In this case, it is the average distance that the molecule travels before it collides with with other molecules. We are first going to calculate the probability of an interaction as a function of the position x. So we're going to assume that something, here we're going to imagine that we have a projectile, which is just one molecule of air, and that it is moving through a target, which is all of the other gas. So that our approximation is that we got one projectile and everything else is stationary. This is, of course, not exactly true, but the corrections are small. So we have our effective cross-sectional area, which was pi R1 plus R2 quantity squared, except now R1, oops, you can't quite see that. R1 and R2 are now equal to each other, and they are R. So you get 2R quantity squared, or 4 pi R squared. And then if we have a thin slice of gas, so we're going to imagine that we have some gas here. It has a width dx, and we are shooting our one molecule of gas through this target. Then the number of targets, the number density of targets is the number density in the gas, so the number of gas molecules per unit volume, times the distance you travel through it, dx. So the probability of collision is that number density times the cross-sectional area for an interaction between two molecules. We are then going to imagine that it has traveled a distance x already, and it has not had a collision. What is the probability that it has a collision in the next region dx? So, and I'm going to call this, so P for probability. Probability between x and x plus dx. So that is that I'm traveling along. That's going to be, if I have probabilities, my probabilities multiply. So I first have to look at the probability that I had some, I traveled a distance x without colliding. And then I have the probability that it collided in the next region, in the region dx. But this is just the same as the probability that I collided in x minus the probability that I did not, that I collided in x plus dx. So I'm slightly more likely to have had a collision here than there. Now this is just negative, I should have a capital P, dp dx times dx. So the probability, this is saying that this is a small amount of change in the probability between x and dx. So I can write that as, because this one comes first, this is the negative of the derivative of the probability with respect to x times dx. So cancel them out, it's the small change in probability. And then that means that I have negative, so I now have a differential equation, and we know what to do with this. So I have P of x n sigma over v equals I'm canceling out my dx's here, negative dp dx, multiply on both sides by dx, and divide by p. I rearrange this, and negative n sigma v dx equals dp, and I integrate, and I get that p equals, or sorry, here I should have a dp over p. I forgot my division by p. So here I get negative n sigma over vx equals natural, let me put a plus a constant, let me put my integration constant there. Equals natural log of p, or p equals, now I'm going to call it my actual, let me write this in 2 steps. P is e to the negative n sigma x naught over v times e to the negative n sigma x over v, but I'm going to redefine this and call it p naught. It's just a normalization constant. And then I want my probability, I want the probability that I interact at x equals 0 to be, sorry, the probability that I did not interact yet at x equals 0 to be 1. So that tells me that p, so if I want that to be 1, that tells me that that at x equals 0, I had better get 1, so p naught is 1, and I get p equals e to the negative n sigma x over v. Now, a little clarification on exactly what this is. This is the probability that by the time I have reached point x, the particle has interacted. So then if I want to calculate the average the average distance to interact, I want to take, we will call this lambda, matching with the conventions in the field. I want to take the probability per unit x of an interaction, multiply it by x, and integrate over all x. So this is a probability density. So this is the infinitesimal amount of probability, the infinitesimal probability of interacting in a small region dx, and I integrate over all x. In this case, over all x is from 0 to infinity. So we start at one edge of the volume of gas and move over to infinity. And now here, I don't want p, I want dp dx. So when I plug this in, I'm going to have n sigma over v e to the negative n sigma x over v times x dx. Now, this is a classical mechanics class, and I would actually not expect that you would have had all of the exposure to probability theory. So what I'm going to ask you to do now is not, if this is not familiar to you yet, that's okay. I wouldn't expect you to know it. Take it as a given that this comes out of probability theory. And when you integrate this, so first of all, we should see this total thing should have units of x. So here, this has units of meters squared over meters cubed. This is just a number. This is times meters. This has units of meters, and this has units of meters. So this has units of meters to the fourth over meters third to the cubed to the third. And so that ends up with a units of meters. Yay! That's the minimum requirement for this to be the right answer. And then we do the integral, and there's a variety of different ways to do this. It ends up being n sigma, v over n sigma. How did I do this? I honestly just looked it up in an integral table. The way you would do this if you had to calculate it by itself would be to do u substitution, where this u is x and d, integration by parts, not u substitution. And one function is x, and then so you could do u equals x. That means that du equals 1, dv equals n sigma over v, e to the negative n sigma x over v dx. So v equals e to the negative n sigma x over v. Integrate by parts, plug the limits in, and you will get this answer. I'm not going to work through the calculus here. We can then plug some numbers in and figure out what this is in. Our original question was, what is it for air? Where we asserted that this spacing R was roughly equal to 1.5 angstroms, so 0.15 times 10 to the negative 9th meters. So then we can take, for example, the units will partially cancel out, so we can ask how much we can use a mole of air, and the volume of a mole of gas at standard temperature pressure is 22.4 liters, or 22.4 times 10 to the negative 3 meters cubed. The number of molecules in a mole, 6.022, 6 times 10 to the 23rd. And then we have sigma, which we said here was 4 pi r squared. So 4 pi 0.15 times 10 to the negative 9 quantity squared. And this works out to be 30 nanometers, or 10 to the negative 3 times 10 to the negative 10th meters. Let's check some orders of magnitude here. There is a hidden hidden factor of 10 here. So this is 10 to the negative 2 on the top. So I have 10 to the negative 2 times 10 to the negative 23 times here I've got, this is another 4 pi is going to give me another factor. Actually, 6 times 4 pi is 24 times, is roughly, 24 times 3 is roughly 75. So I'm going to call that another 2 orders of magnitude on the bottom. And then here I have 10 to the negative 9th, actually it's really 10 to the negative 10th, squared, so, and it's in the denominator, so it's 10 to the positive 20th. So here, if I add those orders of magnitude, then I get, this is 10 to the negative 27 times 10 to the 20, so I get something on the order of 10 to the 10 to the 7th. So I get, if I work this out, 130 nanometers, that is 10 to the negative 7th overall. Now, we can take what we've done for when we were specifically considering spherical projectiles and scattering, where we really had this picture in our head of generic scattering. What we said was that the number of scattered objects is equal to the number of incident objects. I've deliberately left that without a subscript. So the number of incident objects times the number density of the target times the cross section. Now we had talked about this in terms of a scattering cross section. So the number of objects scattered is proportional to the scattering cross section. But we can actually change that subscript, and we can talk about whether or not the projectile might be captured or any number of other processes. So here, when we talk about capture, this is, for instance, an electron comes in and it hits an ion, and the electron is captured. It also can refer to a proton or a neutron coming in and hitting a nucleus, and it is captured. Or a neutron coming in and hitting a nucleus and causing fission. So that would be the fission cross-section. And all you're doing is that you're just changing the name of the subscript, and you are basically you're assuming that the number of things, you're using this to define the cross-section. So the number of things that interact in a certain way is the number of incident objects times the target density times the cross-section, and it is effectively a way of defining the cross-section. And you can then, if you have two processes where, let's say that when you have an incident beam of particles on one type of particles onto another type of particles, the projectile can either be scattered or captured. Then you have a total cross-section, which is the effective area for the target, the projectile interacting with the target. And it's just going to be the sum of all of the cross-sections for the other processes. So if you only have two processes, capture and scattering, then the total cross-section is the sum of those two processes. You could also have ionization, where something comes in and knocks an electron out. Really? Just change the subscript. This is your effective definition of the cross-section. And as an example, if you have an electron hitting a chlorine atom, then you have both. You can have an ionization cross-section, and you can have a scattering cross-section, and you can have a capture cross-section. So it's very general, and you can think of it as this equation is how we define the cross-section. Just like when we talked about collisions, we had an inelastic and an elastic type of collision. Here you can have an inelastic and an elastic type of collision. So if you have your projectile comes in and it leaves the target, the internal motion of the target is largely unchanged. So you might have, the target might be knocked out and leave with some momentum, but it's still the same target it used to be, then we call that an elastic collision. If the projectile comes in and it does something so that the target no longer looks like it did before the collision, that is an inelastic collision. And that could be capture of the projectile. It could be ionization. It could be that your projectile comes in and excites the nucleus. Maybe a proton comes in and it excites the nucleus into a higher level, so it's now an excited nucleus as opposed to where inside the nucleus the nucleons are not in their ground state. So that is not the same target as you had before the collision. So then you can define your total cross-section as the sum of all elastic processes plus the sum of the cross-sections of all inelastic processes. I dropped an L there. And then you would have, and that is just additive because the total number of scatterings is going to be the total number of elastic scatterings plus the number of inelastic scatterings. And so this is really saying that your total cross-section is the sum of the cross-sections of all of the different types of processes. You have to be a little careful that you're not double counting because for instance, capture process is an inelastic process, so you can't, it's included in this term here. So far, we've only talked about the inclusive cross-section. What I mean by that is the total number of interactions. So if we go back to one of the earlier examples, you were just asking how many bullets hit a crow, and it doesn't say anything about what happens afterwards or how you divide those different events. So in the case where you're shooting crows, you could divide events to, well, it hits a tail feather, but it doesn't really hurt the bird, or it hits the bird and it kills the bird. So you can divide what happens into a bunch of different events, and you can also talk about what happens afterwards. So if we have our scattered nuclei, you want to see where the projectile and the target end up going afterwards. So to do that, you have to talk about something called the differential cross-section, and we're really only going to talk about the differential cross-section in terms of the angle of the angles that the projectile and the target go into, although you can also measure projectiles and targets relative to many different observables, and all of them are different forms of differential cross-sections. So for this discussion, we're going to at least start by focusing the discussion on only elastic scattering. So you either have then no interaction or the projectile scatters elastically. The concept can be expanded to other types the same way that we expanded the concept of a cross-section to things other than simply pure geometric scattering. To do this, to expand this discussion, we need to talk about something called the solid angle. And you may already have some concept of this. If you're talking about the area of a sphere, you end up, to get the area of the surface area of the sphere, you integrate over the radius squared, and then you have the volume element. Here I'm using phi as the angle around in the xy plane, and theta is the angle from the normal, from the z-axis. And then our limits are 0 to 2 pi and 0 to pi. So then if you integrate this, you get 2 pi from the integral over phi, and then you have negative cosine theta evaluated at pi and 0, which gives you another factor of 2. So you get 4 pi r squared. So then you can create a dimensionless quantity if you're talking about the area, the surface area of a sphere. A over r squared is 4 pi. So no matter how far you are from the circle, no matter how far you are from the center of a sphere, the area divided by the radius squared is always going to be 4 pi. Now, here I happened to integrate over the entire surface area of a sphere, but I could just as well have chosen some smaller set of angles. So I'm going to restrict where I'm going in angle. It doesn't really matter how much I restrict it. A over r squared is going to equal, we call this the solid angle that I have integrated over. So if it is the whole sphere, it is 4 pi. If I integrate over a semicircle, that would correspond. Actually, I could choose a few different ways of doing it, but I could, for instance, change this to be from 0 to pi. So I would get an overall integral of 2 pi. And if I take the area divided by the radius squared, I will always have 2 pi for a half of a sphere, 4 pi for a sphere. The reason this is a useful concept is because you often want to know for instance, if you are capturing light, or you're measuring, let's say that you're measuring projectiles, so you have some collision and it leads to projectiles in many different directions. You want to know what directions you measure. You build a detector here and you subtend this angle. You could move the detector out. You will detect a smaller fraction of the particles. The real thing that determines what fraction of the particles you detect is the angle subtended by the detector. So this is the solid angle, and so if you capture more of a larger solid angle, then you will measure a greater fraction of the of all of the products. This observable, the solid angle, has a unit of a steradian, abbreviated SR. So the same way that when you're talking about an angle, you call it, the unit is radian, but it's actually technically unitless. So when you're keeping track of your units and canceling units out, it can be helpful to keep the unit there, but if it doesn't, but at the end sometimes, well, you use the fact that it's unitless. And so here, when I integrated over the full sphere, I used this. We are going to call this part d omega, a small part of the an infinitesimal amount of the solid angle. And then we're going to look at the cross section, and we're going to look at the cross section into a small segment of the solid angle. So here, I can look at the number of scattered projectiles into some segment of the solid angle d omega. And here we're just going to use our definition of the cross-section, the number of incident projectiles, the number density of targets, and then we have a small segment of the cross-section, and specifically it's the amount of the cross-section that goes into d omega. And I can always multiply on top and bottom by capital D omega. So the number incident times the number density of targets, d sigma d omega into, well, and then times d omega. I'm going to just drop some of the subscripts to make life a little bit easier on myself. And this guy right here, we call the differential scattering cross-section. So in principle, it is telling us the scattering cross-section into this section of the solid angle. Now, if we, just like when we integrated over the full surface area of the sphere, if we integrate the differential cross-section over the full solid angle, then this should give us back the total cross-section. And this we can also write is sine theta 0 to pi d theta integral d phi. If you haven't seen this before, often when we do, so in introductory calculus classes, you usually followed very strict order about where you could put the d phi and the d theta, and you didn't break the order ever. In physics, we often move them around. Just keep in mind that this is an operator, so when it moves through something, it integrates. And so I can't move this on the d phi over here because this is the integral over phi. But I can choose to group things a little bit suggestively. And actually, the reason why I'll do that is because we will later come back to this. Often this differential cross-section for many physical processes doesn't depend on phi. So the total cross-section is the integral over the differential cross-section. So if you have the differential cross-section, if you integrate over all space, you should get back to the inclusive cross-section that you expect. So then we can do an example of the neutron scattering off of a heavy nucleus. And here we're just going to state an assumed form and look at what that leads to. So if the neutron cross-section of a heavy nucleus is some constant times 1 plus 3, and here this is not the total cross-section, it's just a constant. And here this constant is around 30, double check that my notes are right, yeah, 30 millibarns. So then, we want to look at the total cross-section from this. So then the total cross-section, and an example of why you might want to do this is that you actually are more likely to be able to measure the differential cross-section because you have detectors that subtend only certain parts of the solid angle, and you might measure the cross-section as a function of angle, but then the thing that is easiest for theorists to calculate is the total cross-section. So in that case, you want to be able to calculate the total cross-section from your differential cross-section. So to calculate the total cross-section, we are going to integrate from 0 to 2 pi with respect to d phi, and from 0 to pi with respect to theta, but then here we have to have our full solid angle segment. I'm going to put the sigma naught out in front. And this actually works out nicely. If u equals cosine theta, du equals negative sine theta d theta, and my u substitution here, I have my negative sigma naught comes along for the ride. The negative is from here, so my sigma naught comes along for the ride. I'm factoring out the negative sign, and then here I have 1 plus 3u plus 3u squared, and then that changes my sine theta d theta to a du, but I still have the d phi, 0 to 2 pi, 0 to pi, and then negative sigma 0 to pi, and here I have u plus 3 halves u squared plus 3 over 3u cubed, and I'm going to I'll change it back to cosines to put in before I put in the limits. And here I have cosine theta plus 3 halves cosine squared theta plus cosine cubed theta. And then I'm going to evaluate it from 0 to pi. Now, when I square it, on this term, I have a negative 1 squared minus 1. So this term goes away. And I get, I dropped my 2 pi. Negative 2 pi. So I have negative 2 pi sigma naught. And then here, for this term, I get a 2. And for this term, I get also 2. So I have a total of, let's see. Yes, indeed. My math now is right, and my notes are incorrect. I have, actually, it's negative 1 minus 1. So it's a negative 2 minus 2, or a total of 8 pi sigma 0, which works out to be 754 millibarns. We then want some way of connecting what we have measured to what can be calculated, because in science, the only thing that determines whether or not anything is science is if it is testable. If something is not testable, it is not science. So most models, actually, we're going to tell you what the cross-section is as a function of the impact parameter, which we do not measure. So we need some way to relate what we actually do measure, which is usually the differential cross-section, to something related to the impact parameter. So if you imagine, because the impact parameter, so we have some impact parameter where the projectile would go if it kept going, if it had no interaction with the target. And here is the target. and it does something and scatters off with an angle of theta. And we want to, if we want to take a small ring of theta, now typically, if your target and your projectile are both spherically symmetric, there will be a symmetry in the collision so that you have no angular dependence on phi. It's going to be azimuthally symmetric. You also could, so even if you had some structure in your target and your projectile, you usually don't, we do collisions like this where the nuclei are in fact not spheres, but they are typically oblate. They're stretched out. They can be perlate, which is squished, but they do collide with each other, but on average, you will still get something which is azimuthally symmetric because you can't distinguish the orientation of the incoming nuclei in general. So you have no measurement of that, and you're measuring multiple different angles. So typically what you measure is in fact going to be azimuthally symmetric. To go back to the frog example, if we were to collide frogs and poor frogs, here is my terrible picture of a frog, and there is some structure, but I collide two frogs. They're going to have random orientations, so if I average over enough frog-frog collisions, it is still going to be azimuthally symmetric. Now, if we take a small ring or annulus, we can calculate the cross-section in that ring. Because it's azimuthally symmetric, we want the area, because remember a cross-section is an area, the area of that cross-section with a small width, dB, and that cross-section is going to be 2 pi b dB, where 2 pi times b is the circumference, and then we multiply by the width of that ring, dB. So that's going to give me my cross-sectional area. That also has to equal 2 pi sine theta d theta. And that means that I can relate theta and b and actually, I'm going to divide through by 2 pi sine theta. And I'm really going to focus on this part. So now d sigma d theta is, here actually, let me write this in a little, so here I take this equality, I don't want to, and I'm going to divide both sides by 2 pi. I have completely screwed up this, along with screwing up the English language. This is my d sigma. My d omega is 2 pi sine theta d theta, and then I'm going to take the ratio of those two equations. D sigma d omega is b dB over sine theta d theta. And here I have to take an absolute value sign because this derivative can be negative, but the cross-section, because it is an area, the cross-section has to be positive. Okay, so this gives me a way to relate the the differential cross section, which is likely what I measure, to the impact parameter as a function of theta. So here, if I know the angle, if I can theoretically describe the scattering angle as a function of the impact parameter. So I say, well, I know where this projectile should be scattered as long as I know what the impact parameter is. That gives me a way to calculate the differential cross section. So if I know this, I can calculate this, and it gives me a form for the differential cross section. An example is hard sphere scattering, the easiest thing to think of conceptually. So then, let me switch colors so it's highlighted. I have a sphere. I have, I have a sphere, I have a center of a sphere, I have a projectile. It comes in with some impact parameter B. And if I have hard sphere scattering, the angle of incidence is equal to the angle of reflection. So these two angles are equal. If this is alpha, then this exactly splits those two guys up, and these guys are all alpha. But my scattering angle is not alpha, it is theta. So then I can look at this and say that my impact parameter is equal to the radius of the sphere, this guy here, sine alpha. So far, so good. And then theta is equal to pi minus 2 alpha, because this is 1 alpha, 2 alpha, and theta is pi minus 2 that, because this guy's pi, 1 alpha, 2 alpha. All right, so my impact parameter is r sine of pi minus theta over 2 trig identities gives me r cosine theta over 2. So now I have b as a function of theta. So I can take the derivative db d theta, and I get r times negative sine theta over 2 divided by 2. And then I take the absolute value, and I put it in here. And specifically, I have to have b. b is r cosine theta over 2 over sine theta times r over 2 sine theta over 2, or r squared over 2 cosine theta over 2 sine theta over 2 sine theta, except now using those trig identities that we all love to forget, this is equal to 2 sine theta, and this cross section is this is equal to sine theta over 2. And this total cross section is r squared over 4. So if you have hard spheres scattering off of each other, this tells you that the differential cross section, the number that you have per unit area, is a constant. And that's actually rather interesting because it is measurable. It tells you that this is isotropic. And then you can calculate the total cross section. This is the integral from 0 to 2 pi, 0 to pi, r squared over 4 sine theta d phi d theta. This integral gives you a factor of 4 pi, so this gives you r squared times pi. So this gives you a very concrete prediction that if you have hard spheres scattering off of each other, well, first of all, there's two clear predictions. The differential cross-section as a function of solid angle will be constant. The distribution of scattered spheres is isotropic. And second of all, the total cross-section is just r squared times pi. So if you did have pure hard spheres scattering off of each other, you could use this to measure the radius of those spheres. Now, of course, this doesn't really happen with any of our subatomic particles, but I like this example because it shows you how you can take a model for collisions, in this case hard spheres, use it to calculate a prediction for the differential cross-section, which gives you two things that are actually very much measurable. You can measure whether or not your differential cross-section is a constant as a function of the angle, and you can measure, you might not always know the radius of your sphere, but you can at least get a good handle on whether or not this even looks close to the right answer. This brings us to, of course, Rutherford scattering, which I know that you guys were all waiting for since we started this chapter. Rutherford scattering is, of course, the way that we discovered the nuclei, the way that we discovered that atoms are not in fact hard spheres with a fixed large radius, but that there is something inside of them. Because note that we had a concrete prediction for what would happen if you collided two hard spheres, and that was not what was measured. You did not get totally isotropic distributions of scattered projectiles, but instead saw that most of the time the projectile went straight through the foil, and sometimes it scattered back, sometimes with very large angles. So we're going to use the same rough angles. So here we have the angle theta, which is the angle of the outgoing momentum. And actually, this is important. There's a variety of definitions of variables. We have our impact parameter B. We have the incoming, so the projectile momentum P. Its incoming momentum is going to be P and its outgoing momentum is going to be P prime. And we will look at, so the target, we don't actually measure. So in the case of Rutherford scattering, you're not measuring the outgoing nucleus, but you are measuring the alpha particle, which is coming in and scattering off of the nucleus. And there is an angle. So if you have deflection from the Coulomb force, at the point, you have a vector u, which is perpendicular to the trajectory at the point of closest approach. And then we have the angle psi. Now, we want to write the change in momentum. So we have the incoming momentum, the outgoing momentum, and then the change in momentum. And this, you can move your vector P over here, and you will see that this angle is theta. And because we can bisect this angle and create two right triangles, then you can see that the magnitude of delta P is 2p sine theta over 2. So in this case, and this should be P prime, so here, this is our vector P, and then we want half of that. And then we are going to write the Coulomb force. We're actually going to write it a little more general, so it's KQQ over R squared, but we're going to write it as gamma over R squared. This actually serves a function because here it is the Coulomb force, but you could equally well have gravity. So many chapters back when we calculated what would happen when you have how you end up with orbits around a central mass. You had a force that had the form gamma over R squared. Now you have a different force that has the form gamma over R squared, and the difference is that the sign, when it is a gravitational force, it is always attractive. When it is an electromagnetic force, it can either be attractive or repulsive, and either way, you get the different classes of solutions. You get hyperbolas, ellipses, and parabolas. The math is all the same. We're not going to derive the orbits here. We're going to derive the scattering cross-section. And then we can write this force. The magnitude is this, and then we are looking at of course, the change in momentum is going to be the integral over the force. This is the magnitude of the total force, but then we want the component of the force in the u-hat direction. So the force that is along, we can treat this like a radial force, and the component that is along the that is parallel is not going to change the angular momentum. We want the component that is perpendicular. The u component is gamma over r squared cosine psi. So just looking at the component, which is, so here at this point the force is in that direction, and we want the component of the force in that direction. Now, because at this point you're reasonably good at calculus, dt is the same thing as d psi dt. Let's see, dt is the same thing as d psi over d psi dt, or d psi psi dot. And this begins to look very similar to what we had when we looked at angular momentum. So this is a central force. It will therefore not change the angular momentum. Angular momentum is conserved. Angular momentum is mr squared psi dot, but it is also equal, so that's equal to L. It is also equal to the impact parameter times the momentum, because you have just the moment arm r cross b. Well, r cross the momentum. And the r is the radius from this radius here is b. So we can use this to get psi dot equals bp over m r squared. Now, we want to look at the change in momentum. By the way, I wouldn't expect you to come up with this derivation entirely on your own without looking at notes. That has to also equal to the integral of f, of the u component of f, dt, and we can now write this is, the u component of f is gamma over r squared cosine psi. Our dt, we are going to write as d psi over psi dot bp over mr squared. And the limits are from negative psi naught to psi naught. So psi naught is going to be what happens when the projectile is way out at infinity. It approaches essentially at zero angle. And then the maximum psi is the point at which it goes off after scattering. Now, this looks kind of hairy and ugly, as things in this topic, whenever you're doing classical mechanics, they are wont to do. But it simplifies. So now I have psi over, my r's cancel out. I end up with an m, and I have a b and a p. And now my integral is negative psi naught cosine psi d psi. Well, that's actually a lot easier to work with, isn't it? Because I know how to do that integral. This gives me a negative sine of psi naught minus, and here I had to actually take the absolute value, negative sine of psi naught minus sine of minus psi naught. So I get a, inside, let me just keep my absolute values everywhere, make it nice and neat. This is a negative 2 sine psi naught. So then this sine of psi naught is also equal to, this should have had in my diagram, okay, so here, because psi naught equals pi over theta minus theta over 2, this guy here I can replace by cosine theta over 2. That is just some dumb trig identities. So the change in momentum is 2 gamma m over bp cosine theta over 2. And I also have, that is equal to 2p sine theta over 2. I can solve this for b. My 2's are going to cancel out here. Boop, boop. And I get b equals gamma m over p squared. And here I have a cotangent theta over 2. It's a cotangent because I have cosine over sine. And now, the very last part of this, d sigma d omega is equal to b over sine theta db d theta, absolute value. And now I have this expression for b, and I can take the derivative of that. It's been a long day. I'm going to leave that as an exercise to the student, which is, so the book actually doesn't go through any additional details. But here I get d sigma d theta equals 1 over 2 sine theta over 2 cosine theta over 2 gamma over mv squared cotangent theta over 2 gamma over mv squared 1 over, I got to make sure that fits on my screen, 1 over 2 sine theta over 2. That is a gnarly mess. Of course, you had to take the theta derivative of this and then plug this guy back in there. And gads, here this one is expanding out sine theta so that it's all a function of theta over 2, so that things cancel out nicely. And you can put back in the gamma and you get k q q over, here this is also replacing the energy is 1/2 mv squared. E 4e sine squared theta over 2. Now, there's a variety of different derivations of this equation. You may see it in electricity and magnetism as well. This is another example where you take a model for your projectile and your target. You're assuming that they are more or less spheres that interact with only through their charge. Actually, it doesn't have to be a sphere. You basically treat them as point charges or things that can be approximated as point charges. Chug through all the math, and it gives you a very concrete prediction for the angular dependence of the cross-section or the differential cross-section. And that was indeed how Rutherford scattering was done, and it was detected that the nucleus is not a hard, the atom is not a hard sphere. There is a small projectile that acts like it is a very tiny point. It effectively, for the level of precision with that experiment, was a point charge. So, of course, Rutherford scattering was confirmed in the experiments done by Geiger and Marsden. They used a pencil beam, and what is meant by a pencil beam is that it is very narrow. It is, of course, there's a finite extent, but it's pretty narrow, and it was shooting straight towards a target. You can create a pencil beam by taking an isotropic source and then blocking most of it. They varied the target in order to measure the Q dependence. You can't always vary the energy of the alpha source, but you can measure it. And then you can look at, given this formula right here, you can rewrite this. I was lazy, I just left it on the bottom, even though that's maybe not the easiest place to see it. You can write this as a component which is energy dependent. This is different from the sigma sub 0 that we had earlier in a problem. And then divided by sine to the 4th of theta over 2. So then, this is example 14.6. So we can then rewrite d sigma d omega. Actually, got that written right there. So we can write the energy dependent part, sigma sub 0 of E is KQQ over 4E quantity squared. And for the, we can actually leave this in electron volts. So for alpha scattering, then we have 2, it's alpha scattering off of a gold nucleus, 2 times 79 times Ke squared over 4E. And if we leave quantity squared, if we leave everything in electron volts, Ke squared is 1.44 MeV, so 10 times 10 to the 6th electron volts. And then for an incoming beam of 6.5 mega electron volts, this turns out to be 0.766 barns per steradian. It has to have per steradian because we're going to use, we're going to get a differential cross section. And then if you evaluate this, what you see, it's got a dependence on sine of theta over 2 to the 4th. So when so when theta is small, this blows up, and when theta is close to 0, this goes roughly to 1. So when theta is very close to 0, you're going to have something really close to this number. And when theta is very, very small, that's when you're going to get a very large cross-section. That kind of makes sense if we go, so you have a large cross-section so if you have an alpha particle smash into a gold nucleus and the alpha particle is very light, that's going to tell you that most of your particles are going to keep going pretty dang close to straight. Whereas what might actually be the more interesting part is the stuff that scatters back that has a very large angle, that has a very small cross section. So that means it's very hard to measure scattering at small angles because it's very rare. So then at 150 degrees, so pretty dang far back, this has a cross section of 0.88 barns per steradian, and at 5 degrees, where things are mostly plowing straight ahead, this has a cross-section of 2.1 times 10 to the 5th barns per steradian. So most of the stuff that you want to measure is very rare. The order of magnitude difference really leads to a huge problem. So to give you a sense, we can then look at the target density, and that is the density of the metal times the thickness of the metal divided by the mass. And so this is going to give you units of numbers of particles per unit volume. And in in the Martzen-Geiger experiments, so you have a density 19.3 times 10 to the third kilograms per meter cubed. These densities and the fact that you always get things by times 10 to the third, this is why chemists tend to use CGS, or centimeters, grams, seconds, instead of MKS, meters, grams, seconds. And then here the thickness was about a micrometer. And the mass of one gold atom is 197 atomic mass units times 1.66 times 10 to the negative 27 kilograms per atomic mass unit. And this gives you a number density per meter squared of 5.90 times 10 to the 22 per meter squared. Now, of course, a meter squared of a foil is huge. So you don't have a real foil that large, but this is where those SI units are not describing things on the order that we actually measure when we're talking about subatomic particles. And then a small segment of the solid angle. They used a square target with a width of 1 millimeter. So you've got 1 millimeter squared, and the screen was 10 millimeters away. So their solid angle, which was subtended, was 0.01 steradians. So that's actually, remember, the total amount of solid angle, if you were to measure everything, is 4 pi. So here, they're not measuring very much of the cross-section. But you can move the target, you can move the screen around so that you can detect different parts of the cross-section. And then you can look at the number of alpha nuclei which were actually scattered. this is the number incident, and times the number density of targets times d sigma d omega times the actual solid angle and then for the this is given as the number per minute, so instead of an absolute number, it's actually a rate. The book uses numbers, but it describes rates in words. So the source was giving 6 times 10 to the 8th alphas per minute, and this corresponds to a rate of scattered alpha nuclei of 31 per minute if you are at 150 degrees, but 7.5 times 10 to the 6th per minute when you are at 5 degrees. Now, of course, at this point in time, they were counting. They didn't have the fancy detectors that we have that automatically do the counting. So, here, this you can at least count. This one is hard manually. You can count to 31 in a minute. This one you can't actually count. So that is actually a way in which maybe it's easier to measure here when you're doing some of these measurements by hand. Now, if you look at the overall cross-section as a function of this angle on a semi-log scale, so log d sigma d omega, this is where you see that this is sharply falling. I haven't reproduced figure 14.13 quantitatively, but it's showing you that that's the rough shape of the cross-section as a function of angle of theta, where this is on a log scale. This is why you need high rates in order to be able to measure this little tail right here. Now, of course, we'd never have particles that are truly at rest. So far we've talked about having a projectile come in and smack a particle which is completely at rest. But what we actually have is that we have an atom inside of some foil. So, we're also approximating, assuming that there's no electrons in there. Usually this is a pretty good approximation, but inside of that foil, the nucleus itself of the nucleus of the atom can be vibrating somewhat, and it is not truly at rest. So we often would rather use the center of mass frame. In the center of mass frame, of the projectile and the target, the motion of the projectile is just the difference, the position of the projectile is just the difference in the positions of the two. We also use the reduced mass. These concepts have come up earlier, but we usually can't really do the experiment in a center of mass frame. We actually do it in a lab frame. So we want to relate the center of mass frame to the lab frame. So we want to relate d sigma d omega in the center of mass and d sigma d omega in the lab frame, where this is actually what we measure, but usually this is what we actually are able to calculate. So we can go back just to understand how this works and look at our Lagrangian in the center of mass frame, it's going to be 1/2 m big R dot squared plus 1/2 mu, the reduced mass, little r dot squared minus the potential of the two particles as a function of the position of the two particles. So Lagrange's equations are going to tell us that the momentum is given by mu r dot, and since there are no forces acting on the system, big R is 0, and this tells us, and then we also know R1, these are from the definitions of R1, or sorry, the definitions of big R and little r. R1 is big R m2 over m little r. R2 is big R minus m1 over big M R1. This all goes back to the chapter where we talked about the center of mass in preparation originally for the use of rotations. Now it's also useful for talking about cross sections and scattering. So, because big R dot is equal to 0, R1 dot, and we typically use, again, 1 is for the projectile, is m2 over m r dot. This marker is tired and needs to take a nap. And R2 dot is equal to negative m1 over m r. So now P1 is equal to mu r dot, and that is equal to negative P2, which is equal to mu r dot. So is equal to, yeah. So this just tells you that the target is coming in at mu r dot. The position of one of the particles, this is just from the definition of R. And then so in the center of mass frame, the projectile is coming in one direction, and the target is coming in the opposite direction. And they both, in the center of momentum frame, have a momentum mu r dot with magnitude mu r dot. So it acts like a particle of mass mu is scattering off a fixed target, as opposed to acting where this mu, so the reduced mass, as opposed to having a particle of mass m1 scattering off of the fixed target. Everything else is mathematically the same. So then we want to come up with relationships between the cross-section in different frames. And we're going to go back to our old definition. The cross-section is defined by the number of scattering particles equals the number of scattered particles equals the number of incident particles times the target density times the cross-section. Now, what's different is that I can add a bunch of subscripts to this, and I can say that this is the center of mass number of scattered particles, and just add different subscripts to everything. I can say lab, lab, lab. All I've done is write subscripts. This will be true independent of the frame that I am working in. Now, if you're talking about the total number of events everywhere, the number of scattered particles will be the same in the lab as in the center of mass. So this will be the same, this will be the same. And that implies, because the target density is also going to be the same in both, that's going to imply that the overall cross-section, the inclusive cross-section, is going to be the same in both frames. That is both enlightening and useful because, of course, typically what we actually measure is the differential cross-section. But what is not generally true is that the angles in the two different frames are not the same, very much not the same. And the solid angles in the different frames are very much not the same. So that means that we have to work this out some other way. Now, the number of, I can write an equation like this in each frame, and I can write it even for a specific solid angle. The number of scattered particles into a given solid angle is equal to the number of incident particles times the number density of the target times the cross-section, the differential cross-section, times the solid angle. So all I've done here is say I'm restricting this to a specific solid angle. And then this is going to work in both the lab frame and the center of mass frame. So I can divide through and say, so here, the total number of scattered particles has to equal the same amount in either way. And the number of incident particles is the same. The number of target particles is the same. So the total number scattered into a given solid angle has to be the same. So I can write that n sigma d omega in the center of mass has to equal d omega. That was my tired marker. In the center of mass. So basically, this stuff is the same, and these guys are the same. So this product has to be the same. So that tells me that d sigma d omega, the differential cross-section in the lab, has to equal d omega in the center of mass divided by d omega in the lab times d sigma d omega in the center of mass frame. So this kind of makes sense because the number of events is the same, but the solid angle actually changes. So then I can write the sigma equals sine theta d theta d phi, except that the d phi part doesn't change very much. I'm going to wrap this into d negative cosine theta d phi, and if I take this ratio, this is telling me that the cross-section in the center of mass is equal to, we got to take an absolute value because the cross-section is always positive, d, the negatives will cancel out for the ratio, d cosine theta, to double check here, I want center of mass, d cosine theta lab. So then I can take, if I know or have measured, if I have a prediction for the cross section in a center of mass frame, I can get the cross section in the lab frame simply by knowing the conversion between the two frames, and vice versa. Okay, so now I want to relate the angles of the lab frame and the angles of the center of mass frame. So here I'm going to use the unprimed, I'm going to use the primed momenta for the incoming, or sorry, it's primed momenta for the outgoing, primed momenta for the incoming, unprimed momenta for the incoming, primed momenta for the outcoming, sorry for the confusion. So if it when this is in the center of mass frame, we have something coming in with a momentum p, and we have something, the projectile and the target both come in with a momentum p, and they both leave with a momentum p prime, a magnitude of the momentum p prime, and then this is the scattering angle, theta, center of mass. In the lab frame, we have P lab 1, P prime lab 1, and P prime lab 2. Now, in the center of mass frame, all four momenta have equal magnitudes. We will assume the lab frame has particle 2, or the target, at rest. And then R1 equals big R plus M2 over M, and a similar equation for R2. My markers are tired. And since particle 2 is at rest, then in the lab frame, then I get that R1 dot, so R2 being at rest in the lab frame implies this. R dot is M1 over M R dot, which is the same thing as mu over M2 R dot, which is P over M2. P1 in the lab frame is M1 R1 dot, and this is just from here. Now here, there I dropped a R. I have M1 over M, and then I have an M2 over M, and then I have an M1 r dot, but this is just p. And this r dot is p over m2. So this is m1 over m2 plus 1 times p. And we are going to use this to define the variable lambda. We call this lambda plus 1p in the lab frame. And in the lab frame, P1, P lab 1 prime is going to be lambda p plus p prime. So this is just using our equation that we can always convert from R1 or R1 dot by adding this factor, and lambda p, we convert to the lab frame by adding lambda p plus the momentum. Then from there you can draw a figure A, B, lambda p. These are the sums of the momenta. P prime lab 1 p prime, and this is theta lab, this is theta center of mass. This is left as an exercise for the student, which always means that it's a lot of ugly, dumb, or it usually means, especially in this book, that it is a lot of dumb, ugly algebra. And you can get this expression. Now, you can see from this figure that the lab frame is always going to be less than or equal to the center of mass frame for the scattered projectile. So you can always go, so basically the center of mass of the system is going to be moving forward because you have a target which is at rest and a projectile which is moving. So the whole system is going this way. That's your momentum of the system is this way. And so you add that to the momentum in the center of mass frame, it's always going to be pointing more towards the direction of the incoming projectile. And then here, if the masses are equal, lambda is 1, and this simplifies so that the angle in the lab is exactly half of the angle in the center of mass. So that sort of makes sense that if your masses are equal, this is equal to P, and P is equal to P prime. So these two lengths are equal. And then we can take this back to what we were ultimately after. And here, again, I am totally leaving this as an exercise for the student because it's really kind of hideous. You can take the result for take this result relating the angle in the lab to the angle in the center of mass frame and get d cosine theta lab, d cosine theta center of mass is an ugly expression. And this is, in fact, what goes into your cross-section equation. That is going to involve a lot of ugly trig identities, but it tells you d sigma, d omega in the lab frame is equal to d sigma, d omega in the center of mass frame, which is the thing that you are most likely to actually be able to calculate, times this factor. What we see out of this is it's a lot of ugly algebra, but you can at least in principle do it to get a generic expression relating what you have actually measured to what you were able to calculate theoretically with just some complicated but straightforward geometry. And that's ultimately what we're after. Now, this expression is worth codifying into a book because this comes up so often.